Okay, so here's the second half of the lecture on power. Just talking about effect size. We've talked about effect size a little bit. This is the size of the effect. Okay, so remember a null hypothesis. You may reject a null hypothesis in favor of an alternative hypothesis saying that mu is actually greater than a certain number. It's greater than 0 or whatever you specified as your null, the mu value of mu under the null. But an effect size kind of tells you, okay, it's greater than, well, how much greater is it actually? What's the actual size of the effect? And there are multiple measures for it. One measure for effect size that we've talked about extensively is r squared, okay, the percent of variation in one variable that's explained by another. Here's another measure that we'll introduce, okay, d. So this is a measure of distance between the null and alternative hypotheses, the mu's under the null and alternative hypotheses in units of standard deviations. Okay, so this is what the formula looks like. Okay, you've got mu1 minus mu2. There's a distance. What are the units? Standard deviation. So you divide it by standard deviations. This is basically the numbers per, or standard deviations. Oh wait, yeah. Number of standard deviations that you can express this distance in. Okay, so it's a pretty simple formula. And I probably won't have you calculate it yourself. You will see D in the literature as a measure of effect size. So this is sometimes, this is often called Cohen's D. And I guess sometimes it's used in slightly different ways. But yeah, Cohen's D is a measure of effect size. Okay, so going back to this question, how many volunteers do I need to recruit for my research project? One of the things that you'll need to answer is effect size, okay? And I'll get to that in a sec. What is a reasonable level of power would be the first question, okay? What is the probability that I want to be at for making the correct decision, okay? 80% power, 0.8, is the level of power employed in the textbook. That's, I assume, a generally acceptable level. A higher power is better. And remember, this is not the same as 1 minus alpha, but which, if you use the typical convention of 0.05, then that's 0.95 would be 1 minus that, but that's not power, it's 1 minus beta. It depends on much more than just your alpha. It depends on the anticipated effect size, the sample size, all those other factors. Okay, so if you can get a higher level of power, that's great, but you need to think about practicality. Okay, and the main issue of practicality is sample size. Okay, I'll show you a table that kind of sums all this up in just a sec. So you need to determine what is the anticipated effect size, basically the distance between those two distributions. Now, you don't know what mu1 and mu naught, or you don't know what mu1 actually is in the real world, right? So you need to kind of get an estimate for what that distance would be, okay? What the effect size would actually be. So hopefully you can look at some prior research to get an actual calculation of D, and you'd actually just substitute, sample means and sample standard deviations for those, for these numbers here in this formula to get an estimate for D. Okay, so it won't be the true D, but you can get an estimate from prior research. Okay, so that's the best thing you can do if there's prior research that aligns well enough for the research project that you actually want to do. Okay, you may also just think about what's the effect size that would actually be meaningful in the real world if you're trying to compare like some new therapy versus another one. You want to see how much it lowers depression severity. You might ask, well, what's a clinically significant reduction in someone's HAM-D score, Hamilton Depression Rating, and then you can say that's the effect size that is meaningful to me. So that's what I'm going to go after. Okay. Now, if you can't really answer those questions, then there are some guidelines, some rough guidelines for small, medium, and large effect sizes. And you can just kind of say, well, I want to go after a small effect size or a medium or a large effect size and just kind of go from there. But that's not as ideal. It's best to get a good estimate for what kind of effect size you could anticipate. If you're trying to look at the effects of some stress manipulation on reaction time, then look at previous research that has shown how similar stress induction protocols have influenced reaction time and to what extent, what kind of effect sizes were other studies showing that were similar. So this is a big part of, like, when you're doing a capstone research project, you need to do some research on what are similar studies that have actually been done previously. Okay. And then to calculate, to get power and to get n, you start with what's a reasonable level of power, but if you need to determine your sample size from that, then you need to determine, well, what kind of test are you actually going to run, because power is calculated in different ways depending on whether you're using a one-sample t-test, a matched pairs, a two-sample t-test, or various other kinds of tests where you want to get an estimate of power. So you need to determine what kind of test you'll need to run before you actually do the research. So that's where that decision tree comes in, right? Okay, so here's this table from your textbook, and this is just to give you a feel for if you are planning a research study and say you anticipate a small effect size, and so you're doing a one-sample t-test, you're going to need 196 subjects. Now, maybe that's doable, but maybe it's not. Typically, the bill for a research study depends a lot on how many subjects you recruit. So you might not have the resources to recruit that many. If you're looking for a large effect size, if you have a research question in which you anticipate a large effect, then you don't need as many subjects to be powered at the same level. So this is all for a power of 0.8, but it's just looking at the effect size, the anticipated difference between the hypothesized null, the hypothesized mu under the null versus the hypothesized mu under the alternative hypothesis. So this is where you're kind of asking this question, do you have the resources to look for small effect sizes? Okay, and maybe you do, but oftentimes you might not have the resources to recruit 196 subjects. Or if you're doing a two-sample test, you got to get 784 people. Now, sometimes you can do that, but that's something you'll need to consider. Okay, so you may not have the resources to do research studies in which you're looking for small effects, these subtle little things. So you might need to adjust your research question and think through what are the questions that are going to show a big you would anticipate showing a big difference. Okay. Here is an online applet that I found that can allow you to calculate sample size for a given level of power with a given type 1 error rate, and then the mean under the null hypothesis, and then the mean under the alternative hypothesis with a certain standard deviation. Now, I've just made these easy numbers for calculation, so these numbers here, hopefully you could get from some prior research. So maybe you had you find a study in which the control group had a mean score for some rating of 20, and the standard of care was 15. So that's kind of the mean rating for that score, or whatever it is, under the standard of care is 15. And then they have a standard deviation of 5. Okay. Type 1 error, usually you'll just have that at 5%. Let's say we want 80% power, and then so that's a pretty big effect between those two, and so you'd only need 8 subjects in that case. This is for a one-sample t-test. Okay, the example from the textbook is like weight gain over the course of a treatment for anorexia, so maybe it would be 0, and then so you're trying to replicate that study, and they lost 3 pounds overall. If you wanted to replicate that study where you're anticipating similar effect sizes, then you would need to recruit 22 subjects, which I think they had about 20 in the first one too. Okay. Now, just to kind of demonstrate here, if you want higher power, let's not double it. Let's say you want 0.9, power 0.9, then you got to get some more subjects. So you want even higher power, 0.95, then you got to get 37. And this kind of shows you, a nice graph showing sample sizes under different levels of power and how many you would need. Now, let's say you're going after just a very small effect size. Okay, where there's a therapy that you're thinking is only going to lead to a gain of 1 pound. Okay, let's go back to 80% power here. Then you're going to need 196 subjects. Okay, so this is, and I think I actually hit on the 0.2 right here, 1 divided by 5. And you're going to need 196 subjects, so that might be too many. Okay, so the link, I'll post this in the slides. This is a calculator that you might find useful later on. All right, so there's the link to that, which I'll post in the YouTube description, and also I'll post these slides. So hopefully, after some practice, hopefully today you're getting closer to feeling like Power Rangers when we talk about statistical power.